All right. Hello. Welcome to class. Tuesday, April 7th. Um, so, a few things to talk about. One, officially, this Friday is not a day off, even though it says it on the calendar. I guess it's a makeup day still. I'm still not going to post anything or make you do any work during that day. So, it's officially a work day. If you have any light work, you can work on it then. But yeah, I'm not going to officially post anything you have to do. Another question I got was about the test. I still have some people who haven't taken the test, so I'm not releasing the key yet. Uh, and I'm waiting on Miss Chuma's classes to take the test. They're taking the same test. So once she gives out the test and once I get a few more people to turn in the test, I'm going to put the key out. So yeah, just keep an eye out for that. I would look at it because I don't know exactly how grading is going to work, but if we do end up having a normal final exam, those types of questions will be on there. We'll see how that all ends up working out. Um, yeah, so today we're going to keep working on Coulomb's law problems. We did some notes on those last class, and I assigned the homework there. So when you finish this, you're going to turn the homework into the other day's work. If you notice today's assignment doesn't have a due date, you're going to turn it into the one with the due date. Um, and yeah, sorry about yesterday. I meant to post tutorials. I don't know if anyone wanted to go to those, but I forgot to post that until like 2 minutes before the time and no one showed up. So if you had any questions then, we can look at them now. So we're just going to keep working through these problems. We're on chapter 18. And if you want to read and take some more notes, at the moment we're looking at 18.1 through 18.3. So it won't hurt to look through your notes on those. This is going to be a solid part of the rest of the year, talking about electricity and circuits. I'm not trying to go too fast, so we're probably going to be on this for a few weeks. And yeah, that's not a lot left over in the school year. So yeah, just try to keep up with that. So the first question, number 5. So 18.2, number 5. I'm probably not going to go through and solve all of it, but I can at least kind of set it up for you. So we did number 6, which was really similar to number 5. So we're looking at a speck of dust in an electrostatic precipitator. So that's a really, really fancy word for a thing that just sucks dust out of the air. It uses electric charges to pull the dust out of the air. It's really similar to if you rub a balloon on your hair, that balloon gets stuck to other things. It uses a similar concept to pull the dust towards it. Um, you could use it for things like that. You can also use this to paint surfaces. They use this for paint for like really precise paint jobs for like a really thin, small coat of paint. Yeah. So we have 1 times 10 to the 12th protons in it and a net charge of -5 nanocoulombs, which, again, like they said, is very large for a tiny speck of dust. So we want to know how many electrons does it have. How can we go about this? Let's just start with we have 1 times 10 to the 12th protons. What do we know about a proton? Positive charge. And what is that charge? Everyone is able to get to Google Classroom. And yeah, sorry if it's hard to get there and do this. I'll go and pull it up for you. So again, if you go to Google Classroom, click on the classwork tab. That's pretty important. Click on the classwork tab, scroll all the way down, and find the formula chart right here. And it's on the very end of the formula chart. So we have charge of a proton, again, Q, charge, positive 1.6 times 10 to the negative 19 coulombs. Again, coulomb is our unit of charge. Charge for a proton, positive 1.6 times 10 to the negative 19 coulombs. We know our net charge is negative 5 nanocoulombs. Again, we're going to have a lot of unit conversions. Normally, I would. Oh, that's the mass of a proton. So a mass of a proton is very useful for some other things. So normally, I would try to make you memorize unit conversions. Obviously, because everything is going to be at home, I can't make you memorize a unit conversion. But what is a nanocoulomb? What is it? Not 9, not positive 9. That's giga. 10 to the negative 9. So this is equal to negative 5 times 10 to the negative 9th coulombs. So we're looking for the amount of electrons this has. If I have a negative charge, do I have more electrons or do I have more protons? Okay, so I have more electrons. All right, so I know the charge of a proton. So I need the charge of an electron. It's very similar to the proton, except it's the exact same number, but an electron is negative. So negative 1.6 times 10 to the negative 19 coulombs. Same charge, but negative. I have more electrons. So if I'm trying to get my net charge is going to be the charge of all of my protons plus the charge of all my electrons, right? That's what net is. You're adding these up. Net force, the sum of the forces. Net charge, the sum of the charges. All right, so I know a few things here. I could put in my net charge is negative 5 times 10 to the negative 9th coulombs. I can get my protons have a charge of positive 1.6 times 10 to the negative 19 coulombs. But that's for one proton. I have 10 to the 12th protons, right? So I'm going to have to multiply this number times 1 times 10 to the 12th protons plus, all right, I have charge of an electron is negative 1.6 times 10 to the negative 19 coulombs. But I'm going to have to multiply this times that number of electrons. So we could use this to figure out how many electrons we have. So I'm not going to go through and do that, as I kind of set up most of this for you. But yeah, so how we approached it. So we were given the number of protons and we were given our net charge. Well, we're given protons. Well, so we know the charge of a proton, positive 1.6 times 10 to the negative 19 coulombs. We got our net charge, negative 5 nanocoulombs, but let's put that into coulombs. We want everything to have the same units. So nano is times 10 to the negative 9. Well, we want to figure out how many electrons we have. If we have a negative charge, I have more electrons. So I need to do charge of an electron, negative 1.6 times 10 to the negative 19 coulombs. Then we use just our definition of net anything. Net just means adding up charges. So net charge is the charge of all my protons plus the charge of all my electrons. So my net charge is at negative 5 times 10 to the negative 9 coulombs. I have 10 to the 12th proton, so I have to multiply that by the charge of one proton, positive 1.6 times 10 to the negative 19 coulombs. Then I add that to the charge of an electron, negative 1.6 times 10 to the negative 19 coulombs, times the number of electrons, and we can just solve for that. Yeah, it's right around there, like 1.03125 times 10 to the 12th electrons. Uh, no, I just wrote extra numbers. In fact, you wouldn't do that. You would use sig figs. So we have 3 sig figs on the nanocoulombs. So yeah, yours would be right. It would be to 3 sig figs. All right, so the other two you had to do were 3 and 4. Did 3 and 4 go okay? So no question. So I guess 3 and 4 went okay. So yeah, so let's keep going. We did number 10 on 18.3. So yeah, now we're going to keep on going with applying our new law, our Coulomb's law. So our electric force is going to be equal to this electric constant, right? Again, this electric constant was K is equal to 9 times 10 to the 9th. A really big number, right? Electric force is a really big force, 10 to the 9th, 9 billion newtons meters squared per coulomb squared. K times charge 1 times charge 2. So the strength of the charges is going to determine the strength of the electric force divided by the distance between the center of the object squared. Again, a very similar formula to Newton's law of gravity. A big difference here is we can be attractive or repulsive. And we're going to see if I do negative times negative or positive times positive, so like charges, we're going to get a positive electric force, and we're going to see this cause the objects to repel. And then if I have a positive times a negative or a negative times a positive, these are opposite charges. So when we multiply this together, positive times a negative or a negative times a positive gives us a negative electric force, and these are going to attract. So we did number 10. Let's just go through. I want to do number 11, 12, and 13. Yeah. All right, 11. So how strong is the attractive force between a glass rod with a 0.7 microcoulomb charge and a silk cloth with a negative 0.6 microcoulomb charge, which are 12 centimeters apart? Using the approximation, they act like point charges. So we're pretty much always going to use that approximation. They act like point charges. So we're going to assume the distance is exactly between the center of those two things. We can't do the math to assume they're not point charges because that would require calculus. So pretty much everything we do is going to make that assumption. So again, pretty much anytime you ever see something that says assume this, it's mostly just making it easier and letting us do the thing we've been doing consistently the whole time. All right, so we have our electric force is equal to, I have my K constant. This is probably going to be the thing that people miss the most. You have to multiply times this K constant, 9 times 10 to the 9th, times charge 1 times charge 2. What is micro? 0.7 times 10 to the So what is micro? All right. So micro is a millionth times 10 to the negative 6 coulombs times negative zero point 0.6 times 10 to the negative 6 coulombs. Again, electric force, like we see, is a really big force, so we're going to be dealing a lot with really small charges. So there is going to be a lot of unit conversion you need to do on here. And then how far apart are these two things? And think carefully. What value are we going to put for the distance between these objects? Or at least tell me what's a okay. So yeah, we need to use meters. So 0.12 meters squared. Again, remember 100 centimeters in a meter. So 12 divided by 100 is 0.12. We'll go through and multiply these. Again, this is one of those ones where I really want you to try to put it in your calculator. I don't know what type of calculator you have at your house, so just try putting this in. A few mistakes I see a lot: not putting this number in here, messing up your scientific notation, times 10 to the negative 6 times 10 to the negative 6, and not squaring this distance value. So everyone should try putting this in your calculator and seeing if you get the same answer I do. Negative 0.263 newtons. Yeah, negative 0.2625 newtons. It is a force, so the units are newtons. And what does that negative electric force mean? Negative electric force. A lot of times negative means left or down, but not for this one. Not quite. It doesn't mean more electrons. In fact, I have a bigger positive charge than I have a negative charge. So because I have a bigger positive charge than negative charge, I actually have more protons than electrons. So if we have a net charge that's negative, that means I have more electrons. But I have a negative force. I got a negative force by multiplying a positive charge by a negative charge. So if I have a positive charge and a negative charge, what could I say those two charges do? Yeah, so this negative electric force is telling me that this is an attractive force. So those two forces are going to get pulled towards each other, is all that can say. And if you notice, they get pulled towards each other, so that means one's going left, one's going right, or the opposite. All right, so if it's positive, we get a positive by doing a negative charge and a negative charge multiplied together, or positive times positive. So these would be like charges, and like charges are going to be repelling. So they're going to be pushing away from each other. My hands are too big. There we go. They're going to be pushing away from each other. So that's all this can tell us. Are they attracted to each other, or are they repelled from each other? All right. B wants us to discuss how the answer to the problem might be affected if the charges are distributed over some area that do not act like point charges. Now, this is probably not a question I would ask you. This is more something I would ask to an AP class. But we can look at it. We're assuming these are point charges, 12 centimeters apart. Now, here we're saying if the charges are distributed over some area. I interpreted this as meaning, so I have a glass rod here, and then I have a silk sheet here. Look at my amazing drawings. I'm interpreting that as saying these are 12 centimeters apart. But I have charges all over the glass. Glass is charged positively, right? So glass, I'm going to have positive charges all over this thing. And then negative charges all over the silk. So what's changing by not assuming these are point charges? Is the amount of charge changing? We're not changing the amount of charge by changing that, right? We're not changing the universe we're in. So if we're not changing our constant, we're not changing our charges, what are we changing? Or distance. Now, a real object has width, so that means some charges are further apart. If the charges are further apart, then what's that going to do to the force? If that average distance between the charges is greater, then our electric force is going to be bigger or smaller. Yeah, so I'm pretty sure that's what they're getting at with this question, is that electric charge, the distance between the charges on average is bigger if the charges are actually spread out, so our electric force is going to be smaller than calculated. It's kind of a tricky question because they didn't tell us exactly how this was measured. If they were really careful with how they measured, if they measured from like the center of this charge to the center of that charge, it would actually work out to where they'd be the same value. So it really depends on what they're saying. I'm not going to really ask questions about that. But yeah, I'm pretty sure that's what they're getting at for this one. All right, let's do 12. 12 is definitely a type of question I would ask. It's a type of question we've seen quite a bit before. So, 12, 2-point charges exert a 5 Newton force on each other. What will the force become if the distance between them is increased by a factor of 3? Right? So this is a question I ask quite a bit. If I double something, what happens? If I half something, what happens? So here, we're keeping the same charges, but we're going to triple the distance between the charges. So first of all, bigger distance, like we saw, bigger distance is probably going to cause a smaller force. Now, we could kind of naively just think, oh, well, we're tripling the distance, so we have a third of the force. What's the problem with that logic, though? Because bigger distance, smaller force. We could just think 3 times the distance gives a third the force. But what part of that equation is messing us up? Yeah, radius squared. So I have 3 times the distance. So radius squared, I really have what amount of force? Not a third of the force, but 1/9 of the force. So yeah, that's a real quick way of going through. We could do that. We can also go back to the method we've done before. when we're looking for this factor, we could say if the value does not change, we're going to put that equal to 1. And we're going to say if the value changes, we're going to plug in the factor the value changes by. So when we do this, so our new electric force is going to be equal to some factor times our old electric force. We're looking at our equation, the electric force is electric constant times charge 1 times charge 2 divided by distance between them squared. So our electric constant does not change. So we're just going to substitute in 1 for the electric constant. All right, it says nothing about changing our charges. So if our charges don't change, we're just going to put in 1 for both of our charges. 1 times 1. But our distance does change. We're increasing the distance between them by a factor of 3. So for radius, I'm going to put in 3. But like we saw, that 3 is squared. So yeah, 3 squared. So my new force is going to be 1/9, right? 1 times 1 times 1 is 1. 3 squared is 9. Times my old force was 5 newtons. So what's my new force? So 5/9 newtons, or if you put that in the calculator, 0.555, repeating forever. Close, but that 5 has to go on for eternity. So I guess not close. Infinitely far from being close. And you'll always be infinitely far away. Who was that guy in Greek mythology that always had to like push the rock up the hill? Forgot the guy's name. All right, so that's really similar to 13. So I'll let you go through and try to do 13. So let's do 14 then, if there's no questions. And yeah, again, the ones that are assigned are under the assignment, and you'll be turning this in on the next one. So 14, how far apart must 2-point charges of 75 nanocoulombs, typical of static electricity, again, static electricity, really small charges. We're going to do one of these, number 15, where we're going to see a really big number, to have a force of 1 Newton between them. So we're trying to find the distance between these charges. So 14. I just got college rolled paper. Do I need to try to write bigger? Or can you all still see what I'm writing? Because I was writing on wide rolled paper before. Been trying to take up more than just one line. Doesn't bother you. I don't know how clear your picture is because some like the one I'm looking at on my TV is a little bit unclear, but then whenever I finish recording, it's a lot more clear of a picture. But I mean, I could use graph paper. I just don't have any on me. All right, so how far apart? So again, we're still dealing with electric force is charge 1, charge 2 divided by distance squared. And the thing you should never forget is that constant, the electric constant. Well, we're trying to find distance. Distance is in the denominator. Anytime we're trying to solve for things in the denominator, it's going to be a lot easier if we multiply this over first. I can't stress that enough. If we're trying to solve for something in the denominator, let's multiply that over first. So our electric force times the distance between the center of the two objects squared is equal to that electric constant times charge 1 times charge 2. Now it should be a little bit more obvious what we do, how we divide the electric force over. So the distance between the two objects squared is equal to the electric constant times charge 1 times charge 2 divided by the electric force. And I can take the square root of both sides. So the distance between the two objects is going to be equal to the square root. Electric constant is at 9 times 10 to the 9th. Honestly, this really is a thing that everyone forgets to plug in or substitute in, whatever. Two equal charges, 75 nanocoulombs. 75 nanocoulombs times 10 to the negative 9 coulombs times 75 times 10 to the negative 9 coulombs. If you're lazy like me, you could just square one of these and then divide it by that electric force of 1 Newton. And I almost guarantee at some point I'm going to make you solve for the radius because out of everything to solve for on that equation, radius is one of the most difficult. And again, try putting this in your calculator because I don't know what calculators you have. You might be using a less than optimal calculator that's more challenging to use than either the Inspires or the TI-84s that you have in my class. So please try putting this in your calculator. You really need to figure out how to use your calculator you have right now correctly. Otherwise, it's not going to be good. Yeah, they do have the calculator apps. Some people are taking their test on the phone though, so I could see that being difficult if like all they have is a phone and then they're trying to switch between the test and the calculator. And I personally dislike touchscreen calculators. I don't know why. But yeah, 0.0071. And because we used coulombs and newtons, we're going to get meters for our answer. Or we could put that in as 0.71 centimeters or 7.1 millimeters. And that's another thing you're going to be seeing a lot of is centimeters and millimeters for distances. What's more, we're converting. But unit conversions are easy. Like those, you just like look at it. Well, that's obviously 0.71 and 7.1. I mean, I just give those to you in those terms because, I mean, when you in the real world, you're not always going to have the units just nicely handed to you in a perfect way. let's say you're actually trying to solve for something and all of your measurements are in inches, you're going to have to convert that if you want anything in metric. Or, I mean, all the times I look up things online to make a test question, I try to, sometimes I have to convert them. Yeah, so the NIMSY sessions, if you are taking the AP test and you went to the first NIMSY session, you don't have to go to those. I would suggest doing them. If you don't want to do the NIMSY sessions, a thing I would suggest, again, if you're in this class and you are taking the AP physics test, look at the AP class. I'm going through 2 old AP questions every single class. I would just look at those and try to do it and then check the key for yourself. You don't have to go through everything they did, but that would be useful. So if you want to do something that's kind of easy but not doesn't take a lot, you could do that. Yeah, the actual district requirement is you need the 4 NIMSY hours, but AP teachers, they've given us kind of leeway where we can do kind of our own thing to say you can do it or not. So yeah, just follow what they say. Yeah, all of those I gave so for all the AP Physics 1, I give the question that is an old AP test question and the rubric for grading it. So I would work through it without looking at anything in the allotted time and then grade yourself on the rubric and then try to get a perfect answer. Shouldn't take a lot of time and it's really useful. And I would skip around to the ones that you're not as certain about. Or even if you don't have time to do that because you're really busy, you could just try to do it while looking at the key. That's less useful, but it takes less time. English is going online. APUSH is up to him. Yeah, when it comes to, it looks like a lot of work. Well, I guess it's less work than normal for AP. But I mean, honestly do what you need to do. Like, don't stress yourself out too much. But I would suggest maybe doing a few of them. It would just be good. Yeah. All right. Let's do 15. Just because I like 15. It really, really demonstrates how ridiculously powerful the electric force is. All right. So 15. 2 equal charges of 1 coulomb each are separated by an air by a distance of 1 kilometer. Electricity is not on the AP test this year. It normally is, but not this year. What is the magnitude of force acting between them? So you'll see even at a distance as large as 1 kilometer, the repulsive force is substantial because 1 coulomb is a significant amount of charge. So again, 1 coulomb is an insane amount of charge. If you're exposed to 1 coulomb, that will easily kill you. Normal bolt of lightning is like 10 to 50 coulombs of charge. So yeah, if you're I cannot stress enough how ridiculously large 1 coulomb of charge is. And it's really 1 coulomb of net charge. I take that back. So 1 coulomb of net charge is a ridiculous amount of charge. All right. So we're just looking for the electric force. And I just like how ridiculous this ends up being. 9 times 10 to the 9th is our electric constant. They say through air, this constant actually changes slightly depending on what the electric charge is going through. Air is pretty much the same as a vacuum, close enough. Times are 2 charges, 1 coulomb times 1 coulomb, or 1 squared. And these are separated by 1 kilometer, right? So 1 squared, correct? No. So 1 kilometer is 1,000 meters squared. Make sure we square that. I don't like writing capital C's. They look too much like a parenthesis. So we have these 2 charges separated by an entire kilometer. And what's the electric force? 9,000 newtons. Or to put this in another way, about 20,000 pounds of force. So you you have these two electric charges 1 kilometer away, and they're exerting a 20,000 pound force on each other about. It's over 9,000. It's exactly 9,000 newtons. Actually, through air, it's slightly under 9,000, unfortunately. But yeah, this is just absolutely crazy to me. Like, that these things are 1 kilometer away, and it would, if you were attached to this 1 coulomb charge and another person was, you just get like launched in the other direction. Um, yeah, it's just a lot. So I can't stress that enough. The gravitational force is extremely weak. The electric force is extremely big. And this is actually really important. Yeah, so we don't have human catapults. It's actually even worse than that again. If the electric force was comparable to the gravitational force, it would just literally be ripping apart your molecules. So we're really glad that's not happening. Or if you were to put the gravitational force at the strength of the electric force, the Earth would just collapse into a black hole. How strong is the output from the wall outlets? So we'll get to this eventually. 1 amp is 1 coulomb per second. So it's not necessarily even how many coulombs flow through a thing, it's how many coulombs are there at a single point. So a lot of your appliances might, let's say you have a 1 amp appliance, 1 amp is going to be 1 coulomb per second. Yeah, so it depends on what your power supply is. So it supplies a voltage. I think a typical phone charger. Yeah, let's see. Here we go. This is a somewhat typical wall charger outlet, and this delivers exactly 1 amp. I don't know if you can see that written on this really small fine print right here. Let's underline that actually. There we go. You can see the little bit underlined in pencil is 1 amp. So this delivers 1 coulomb every second. A thing that's going to be different is, we'll get to this with resistances. So this is how much it sends through the phone. If you were to actually touch this, it wouldn't be able to send that coulomb through your body every second. So that's a difference between these. We'll get to this when we deal with circuits. So even though this sends 1 coulomb through your phone every second, it's not going to be able to send that charge through your body. A lightning bolt will be able to, because it's a lot higher voltage. So yeah, it's not quite as simple as I touch that, I get 1 coulomb. Yeah, you can easily die from the power from an electrical outlet. We'll get into those. You have to do a lot more things, like with multimeters and resistances. But yeah, we're going to get to Coulomb's law, where we'll be dealing with like multimeters and doing things like this. And we have something like current is equal to V equals IR, voltage divided by resistance. So I could go in here and figure out what my resistance is. So I, as a person, have about 400,000 ohms of resistance at the moment. 4 times 10 to the 5th ohms of resistance. So I could look at my wall outlet. The wall outlet has 120 volts, so 120 volts divided by 4 times 10 to the 5th. And so we could get, let's see, if I were to touch the outlet with one finger and touch another thing with my other finger, is what we're calculating right now. 120 divided by 4 divided by 10 to the 5th. So pretty small number, 0.0003 amps going through that. So that's not enough to like kill me immediately, but the problem is if this decided to go through a different part of my body, especially through my heart, it could stop my heart if it went through that specific path with a slightly lower resistance. So yeah, that's more. You're going to be getting a really small number of actually coulombs. So like, yeah, I mean it's a multimeter. A lot of people have these. We were going to use these in labs, but yeah, multimeters are fun. I love electricity. I love circuits, things like that. But we're probably going to do some labs with this. I have like a lot of these. I have a lot of breadboards and resistors that will be playing. Well, I guess I'll be playing with it. Yeah, so she touched too. Yeah, don't. I mean, it's not like. I mean, don't do this at home if you don't know what you're doing. Wait, that's not. Oh, do you not have the high voltage setting? Yeah, let's not do that. I don't want to blow out my big fuse. I was going to jam this in my electrical outlet, but I don't want to blow out a 10 amp fuse. But yeah, if you do it right, you won't blow out the fuse. Yeah, I would have to actually check it. This is kind of like, but yeah, you can do that if you know what you're doing. So yeah, don't do that. But yeah, yeah, nuclear power plant. Because yeah, we worked in that, and yeah, don't do that. Turn the power back on. Yeah, it all depends on where the voltage goes, where the current goes through your body. Yeah, that's how bad it is. Yeah, when it exploded. So yeah, I've again. The problem is there's like a high voltage setting, and I wasn't exactly sure it was on the high voltage setting. I was gonna like look at it a little bit longer. It's more if it blows out the 10 amp fuse, it's more annoying because I know I'd have to order a 10 amp fuse. It just like pops and it makes a lot of noise. But yeah, I probably wouldn't have done that if the setting I was on. I just wanted to be certain it didn't blow up. All right, back to this. What was the next one I was gonna do? Is it 18? Yeah, let's do 18. All right, that's fine. Have a good day. And I'll be here tomorrow at like 1 for tutorials also. Yeah, the rest of this I think I put due as tomorrow. I might change the due date. All right. Yeah, it's at 8. All right, so by what factor must you change the distance between the 2-point charges to change the force between them by a factor of 10? All right. So again, we're going to go to the thing where if it changes, I put a 1. If it doesn't change, or if it doesn't change, I put a 1. If it changes, I'm going to put the factor. So we're still dealing with electric force is equal to charge time, or electric constant times charge 1 times charge 2 divided by distance between them squared. All right, so I want to change the force by a factor of 10, right? You said class today was on a... Did I? I don't know. I'm like losing track of like the days. 10 is my factor I want to change my electric force by. 1/7. Did it? What? Did it say 1/7? It may have. I'm like losing track of months also. Wait, 4/7? This is the 7th. Oh, Monday. Yeah. You know, one year has 4/7 on a Monday. Yeah, I know days real well. All right, K is a constant. That didn't change. So I'm going to put a 1. distance between the two charges. It doesn't say anything about changing my charges, so I'm just going to put a 1 in for those. And I want to know what factor that distance changes by. Probably shouldn't call this 1. Let's just call this some... I'm just going to call this x for my factor. All right, so again, I'm trying to solve for this thing in my denominator. So let's multiply my denominator over. So I have 10x squared equals 1 times 1 times 1. I can divide by 10, right? X squared equals 1/10. Or x equals 1 over the square root of 10. So by what factor must we change the distance between the 2 point charges to change the force by a factor of 10? I could either say the square root of 1/10 is one way of writing this, so 1 over the square root of 10, or I could say decrease by a factor of the square root of 10. And again, B is talking, is explaining how the distance can increase or decrease by this factor and still cause a factor of 10 change. So it's saying if I change by the square root of 10, why do I change the force by a factor of 10? Yeah, radius squared. That's pretty much, and that's all B is saying. It's radius squared. So R squared. I square 10. Square the square root of 10, I get 10. So, and then it's 1/10. 1 over the square root of 10. So 1 over the square root of 10 squared is 1/10. But I divide by 1/10. And then the other thing is just like 1 divided by 1 divided by the square root of 10 squared is just 1 divided by 1 divided by 10 equals 10. Math. Yay. All right, the last one I want to look at is 22. 22 is fun. I'm going to let you read that and think about it for a second and say what you think we should do for 22. At what distance is the electrostatic force between 2 protons equal to the weight of 1 proton? So I'll let you think about how you should start that. Oh yeah, here we go. I figured out the setting. So I could just jam these into my outlet here. And there we go. 124 volts. So yeah, if you know what you're doing, jam things into the electrical outlet. Don't do this. I know what I'm doing. And you saw how much thought I put into that. All right. So the electric force equation. So we do know our electric force equation, but it's not equal to the mass of the electron. What's our electric force equal to? Because that 1.67 times 10 to the negative 27 is the mass of the proton. But I don't want the mass of the proton. I want this to equal the weight of the proton, right? So I want the electric force to equal the weight of the proton. So the electric force is that constant times charge 1 times charge 2 divided by the distance between the objects squared. It's all equal to the mass of the proton times acceleration due to gravity. All right, we're trying to find distance. So again, distance is in the denominator. Let's multiply that over first. So electric constant times charge 1 times charge 2. It's all equal to mass of the proton times acceleration due to gravity times distance between them squared. Then I can divide mass and acceleration to the other side. So the distance between the two objects squared is electric constant times charge 1 times charge 2 divided by mass of the proton times acceleration due to gravity. Now, this is one where I really, really want you to try to put this in your calculator because this is going to be really easy to mess up with all the scientific notation we're about to see here. So this constant K, 9 times 10 to the 9th newtons meter squared per coulomb squared. So the electrostatic force between two protons, so the charge of a proton is positive 1.6 times 10 to the negative 19 times positive 1.6 times 10 to the negative 19 coulombs, all divided by mass of the proton is like what you said, that 1.67 times 10 to the negative 27th kilograms times 9.8 meters per second squared. I like this question because it's like, how high would this thing float? I could easily ask something like this, like two electrostatically charged objects, how high would the object float above the other one? It would be when the weight is equal to the electric charge. So yeah, the other way of wording this would be, how high does the proton hover above the other proton? All right, so what distance do you get? So parentheses are really important here. So when we do our division, let's put our entire division in parentheses. Out of all my sets of parentheses, these are my most important. You're normally going to see your parentheses on the denominator are way more important than parentheses in the numerator. So let's put all of that division into our numerator, and we should get right around 0.119 meters. Or 11.9 centimeters. And again, the other cool thing about this question is it really kind of shows the difference between the electric and the gravitational force. So gravitational force, you need the giant planet Earth in order to pull on this thing, but that entire force of the planet Earth can be easily canceled out with a tiny little proton. So that's just how absolutely massive the electric force is compared to the gravitational force. Which again is why when you stick things in the electrical outlet, they explode. So don't do that unless you really, really know what you're doing. Anyone else having issues getting this, or were you able to get it? Well, keep working on that to try to get it. I'm going to stop the video here so it doesn't keep going. Again, this homework is going to be due at the end of tomorrow. I think that's what I put as a due date, right? The end of tomorrow. Yeah, the end of tomorrow. You are going to turn it under the Friday class, the one that actually has a due date on it. You'll turn in your homework there. And I will have tutorials tomorrow at around 1. I will post the test key when some more people have taken it, or probably towards the end of this week. So if you know anyone who hasn't taken the test, or if you have anyone's phone number or email or anything, just reach out to them and try to get them to take the test so you can get the key faster. And then, yeah, that's mostly it. So this is about the extent we're going to be dealing with Coulomb's law. We're going to go a little bit into types of charging, not a whole lot about that. And we're going to deal with electrical circuits coming up pretty soon. We are really close to the end of the year. It's going to go by pretty fast from now on because this is the last week of what's supposedly the 5th grading cycle. I don't know how that's all going to work right now. But yeah, we only have a few weeks before that like pre-finals week and then the finals week. It's going to go by pretty fast. So other than that, just get this done. Hopefully everyone's having a good day, and I'll see y'all later. I accidentally